All right, so next up is hybrid structures, or most oftenly called resonance structures. And so because we're doing this kind of a model, there's limitations to it. So limitations to drawing structures with lines / dots, right? It's a very simple structure or a very simple model, and so there are some limits to it. But some that we can overcome pretty easily through this idea of resonance or hybrid structures. So for example, ozone is O3. Oxygen has 6 valence electrons, so that's 18 total for 3 of them. So if we draw out oxygen like this, right, we use up 4 of the electrons, so we've got 14 left. And so we can put 6 on each one on the outside and then 2 on the middle. If you've got all the same atom and you're wondering which one to give an octet first, start with the terminal ones first. And so now we've got choices. This center oxygen needs 1 more bond to have an octet. And so we could pull it from here, or we could pull it from here. And so let's see what happens when we do either or. Cool, so there's our structures, and then if we take a look at the formal charges, go ahead, pause the video, find out the formal charges. So we can see that on this structure, the center oxygen is positively charged, and this outer oxygen is negatively charged, while the one on the left is neutral. And then on this one on the left is negatively charged, the one in the middle is positive, and then the one on the right is neutral. Whoops, drew an extra lone pair there. And so we can see we have a negative and a positive charge. Oxygen cannot have more than 8 valence electrons, so it cannot break the octet rule. And so we can't make any more bonds. And in each structure, we've got the same thing. We've got 1 positive oxygen and 1 negative oxygen. So they're kind of the same thing. So they're both equally correct. So what does the real molecule look like? The real molecule is what's known as a weighted average of the two. Sometimes you'll hear that it's a superposition of both of them. And so the way we draw that is we just draw both resonance structures, or all of the resonance structures available. And then we use this double-sided arrow. This double-sided arrow is a resonance arrow. And so with hybrid structures, it's not that the one on the left is right and the one on the right is right. It's that the real one is somewhere in between. It's not bouncing back and forth between the two. It's just somewhere in between. So in real life, both of these bonds are really more of kind of 1.5 bonds. You see, because half of the time it's a double bond, and then the other half it's a single bond. And so the actual structure is kind of 1.5 bonds. And so this is what's known as the bond order. So a single bond has a bond order of 1, a double bond, a bond order of 2, a triple bond, a bond order of 3. Something in a resonance structure has a fractional bond order. And so this one is 1.5, because in half the structure has 1 bond, in the other half it has 2. Let's take a look at another example. Nitrate is probably one of the most common examples for this. So it's got 24 valence electrons. And so when we first draw out the structure, the less electronegative in the center, surrounded by the more electronegative, 6 bonds right there. That's 18 left. That's enough for each one of these oxygens to get an octet. So you're left. So if we think about the charges that are going on here, this nitrogen is actually +2. and each one of these oxygens is a -1. Now, nitrogen cannot break the octet rule. It cannot have more than 8 valence electrons, and so we can only bring out one of these bonds down here to help eliminate some of this formal charge and give nitrogen that octet. And so you can see all the oxygens are the same, so it's kind of arbitrary which one you pick. So for this one, you could draw 3 different resonance structures with a bond coming from each one of the oxygens. So let's take a look at that. Nitrogen has the positive charge, and so you can see the sum of the formal charges is still equal to the overall charge, and then we can draw 3 different resonance structures here. Then one more. Cool. So you can see we have 3 different resonance structures. So what does that mean in real life? Well, in real life, that means that every bond is not a single bond some of the time, a double bond some of the time. That is not correct. What it really means that each bond is approximately 1 1/3 of a bond. Because if you look at any of these bonds, here's 2 bonds, 3, 4 bonds divided by 3 structures. 4 divided by 3 is 1 1/3. So go ahead, do the same with carbonate and think about the bond order as well.